Moving on to task number 2, which is the next hop self. We need to verify the out loopback interface 10 through 12 on all routers can be reached by all other routers. And for the routes that are not reachable, we need to identify the problem and make necessary configuration changes to basically solve our problem. Okay, so let's start off with our router 1. If you do show IP BGP, just to take a minute and go through this BGP table. Okay, from the left, if there's a asterisk or a star at the front, that means the route is valid. And then the greater than sign, it means these are the best routes in case the router has been receiving the same route from multiple neighbors. And then we have our subnet for the routes. And then the next hop, like I said earlier, if it's all 0.0.0.0, that means it's locally generated routes with where there is a network using a network command or a redistribution. The metrics by default are zeros. So if you just receive the route from iBGP, the local pref by default is 100. And the weight, if it's a local routes, it's 32.768, otherwise it's default to 0. And then for the path, I is IGP for the origin. And then question mark, we said it's an incomplete of origin. And then we can also see the AS path that shows the AS number. Okay, so for example, as the router 1 sees the routes that's coming from router 4, what this means is the route has gone through RS0058, which is where the route was originated from, which is R4. So just to show you the diagram right here, AS0058, router 4, and then it came in, or actually it went through 200, so it went across, whether it's this way or this way, going through 200, and then before it reaches R1. Okay, obviously that's not the shortest path because, as you can see, there's a second route right here that's coming directly from R4. So right here, R4 to R2, and then R2 advertised to R1. Okay, so that's why we only see one AS number in the path. All right, so you can see the majority of these routes are valid, and there's also best routes for each of those routes, except for the routes that belongs to R7. As you can see, although it's valid, it's not selected to be used as the best route. Okay, and the reason for this is, if you look at the next hop, these are the IP of the R7 as it advertised to R2, although the route is being advertised to R1 by R2. Since it's an eBGP route, the next hop IP address doesn't get updated or replaced by R2. So as R1 receives the route, maybe I should scroll up, and you can see right here, 172.16.27.7. So as R1 received the route from R2, it still sees that R7 IP as a next hop. Okay, and is not able to use that route because R1 has no idea where that next hop is. So if you do show IP route 16.27.7, you can see the subnet is not in the table. Same thing if you do a show IP ceph, you can see it came back as no routes. Okay, so basically what it means is the next hop is unresolved and R1 is not able to use that route just because it's unknown next hop. Since the problem is basically that VLAN 27 right here is unknown to R1, the most logical thing to do to fix that is to advertise that subnet from R2 to the network. So just to show you how that works, and that is of the interface fast01 on R2. So we go to R2, look at the interface fast01, here's a subnet with interface fast01 to advertise that to the internal routing protocol or IGP using ISIS. We use the command IP router ISIS. Okay, now going back to R1, R1 should now be aware of that subnet. So if we just do up arrow and then show IP route of that one more time, you can see that R1 knows how to reach that subnet by pointing that to R2. Let's take another look at our BGP table. For the R7 loopback interfaces, you can see now that R1 knows how to reach the next hop IPs. It's able to use that route. Okay, so now if you do show IP ceph 7.7.0.1, for example, the ceph table returns a next hop of a R2, okay, which is 12.2. Now if you're trying to ping 7.7.0.1, make sure we source from the loopback 10 that R7 has a knowledge of, you can see that's pingable. Okay, so obviously you can go around and make sure at the edge router like R1, R2 for AS, right here, R1, R2 for AS100, R3, and R6 for AS200, you can basically advertise the external link, or which is the external facing link, back into the ISIS. So all of the other router in the same AS has the knowledge of those links. But there's actually a better way of doing that. Since once you advertise this link, those subnets or routes going to show up in the routing tables on all these routers. And now just to keep the routing table kind of clean, the better way or the proper way of doing that is to have your edge router resetting the next hop IP. So instead of being the first hop of the external or eBGP session IPs, you can have the edge router that receives that route reset the next hop IP to itself before it advertises it to the iBGP neighbors. Let's first revert the changes that we just did for the route from R7. So let's take away the VLAN 27 routes from the routing table and make sure we are back where we were with the show IP BGP. Okay, so it's no longer marked as a best routes. So now what we're going to do on R2 is to configure a next hop or replacement with the command next hop self. So as the routes are being received from their eBGP session, the R2 will replace the next hop attributes by its own IP. Okay, so that way the internal router doesn't need to be aware of all the external link subnet. So we're going to do on R2 under a router BGP 100 with the neighbor command, and it has to iBGP neighbor, which is R1 and R5. So with R1, you can see right here there's a next hop self, which is disable the next hop calculation for the neighbor. So I'm going to do next hop self. And same thing for R5. And now if we go back to R1, let's give it a second. Okay, so let's just take a couple seconds right here so you can see how the next hop IP changed from 27.7 to a 0.2, which is the R2 loopback 0 interface, or its BGP source interface. And now all these routes that belongs to R7 has once again becomes a best routes. Okay, so we show IP Ceph 7.7.0.1. It should be pointing out a 0 interface that connects to R2. Okay, we can do a test ping as well, just to make sure. And those are pingable. Okay, if you jump over to R5, just to double check, with the show IP BGP, the same thing happened here, which is the next hop has been replaced, or the IP of the next hop has been replaced by the R2 loopback 0 interface IP. Okay, now let's go back and take a quick look at the diagram. The other router that we need to apply the same configuration change is R1 right here, since it has the eBGP links, as well as R3 and R6. Okay, for R4 and R7 we don't really care because they do not have iBGP sessions. So let's go through and make those changes with R1. Router BGP 100, neighbor 0.2, next hop self, and then 0.5. And then R3 with the neighbor of R6. So 172.16 0.6, next hop self. And then R6, neighbor of R3, so 16 0.3, next hop self. Alright, let's make sure that these paths or all the routes are valid. Double check with R3. You can see all of the routes as the best path. And let's take a quick look right here. So you can see, for example, the R1 loopback as it's being received from R6, and R6 has replaced the next hop IP with its own loopback 0 IP. Okay, so 0.6. Let's also do a quick check on R6 as well. Same thing happened here as R6 received the R1 loopback routes from R3. R3 replaces the next hop IP with its own loopback 0 IP, which is 0.3. So now going back, we need to make sure that all of the loopbacks are reachable by all the routers. So instead of me going and do a ping one by one from each of the routers to all of the loopback, I've come up with a tickle scripts that we can use. So let me show you with Notepad right here. If you guys are not familiar with the tickle scripts, it's something you can come up with and helps you automate the ping command, which is usually what it's commonly used for. Okay, so you just need to get to under a TLC SH, and then it takes a little bit of a programming. So for each host, it's just basically a for loop for each of the hosts. We're going to perform a ping command, and then it's going to replace the host being a variable by each of these IPs. Okay, so we're going to ping each of these IPs, sourcing from a loopback 10 of the router that we performing the ping on, and then do a repeat of 2. Okay, so everything goes well. All those pings should come back successful. Okay, there you go. Enter. You can see how it runs. As long as we don't get a dot, we know we're in good shape. Okay, so for router 1, all the ping went through. Then router 2. Okay, and router 3. Router 4. And again, the tickle script is usually supported on the router. I believe the newer version of the switch supports it as well, but for the most part, any router or Cisco router should be able to support a running of a tickle script. Okay, now router 5. So far nothing has failed, so that's a good sign. Router 6. And then to complete our tests, router 7. Okay, it looks like we can ping everything successfully from all of our routers, and that's pretty much complete our task number 2.